Hello everyone, we will continue with our lecture series now. We are at lecture number 29 today. A lot of control synthesis, control analysis as well as synthesis techniques we have studied before, both in the classical domain a little bit in the beginning as well as modern control domain quite a lot later on. And then we have also seen this flight dynamics concepts actually before. So, now the question is, can we combine the two and come up with nice flight control design techniques, especially in the context of aircraft control. So, that is the topic that we are going to discuss today actually. So, the topics today is something like this. First we will again quickly very quickly rather we will review the aircraft flight dynamics one more time, just for recapitulating all that thing that we have done before. Then we will also give an overview of automatic flight control systems. Okay. Then we will proceed with the frequency domain design techniques, followed by time domain, but probably the we will cover only up to this today. We will cover like automatic flight control systems with frequency domain design, essentially using some of these classical control design techniques actually. Next class we will follow it up with some of these modern control designs as well. Okay. So, let us see this a brief review of aircraft flight dynamics. Essentially, we have studied all these things before and just a recapitulation of what all we have done before. So, this is geometry of a conventional aircraft. You will see that there are various subsystems of the on the aircraft, and then each of the subsystems have their own role to play. And whatever you see these darkened lines and all that there, these are all essentially you can think of as some sort of a movable parts, they are not fixed part. And by moving these surfaces up and down and things like that, you essentially change the aerodynamics around the surface, and hence generate additional forces and moments, thereby you control the aircraft actually. So, essentially you have these control surfaces elevators right here, okay, and then you have this ailerons, which is somewhat here as well as here, and then the rudder actually. So, rudder is somewhere here. So, these are three primary control surfaces acting on the aircraft. Other things are like spoilers, slats and all that are also there, but they are not very frequently used. They are used primarily while takeoff and landing, but not during flying actually. Anyway, so these are all various components acting on the system. And then basic force balance on a steady and level flight is obviously something like this. We have the weight of the aircraft acting down, so something has to sustain that weight. So, it has to be lift vector, and while producing this lift we produce drag as well, and to counteract the drag we have to produce a kind of a thrust actually. So, this thrust, drag, lift and weight balance each other in a steady and level flight. Side forces are typically balanced out actually. They are not normally there is no force acting sidewise. Okay. Then about the moment balance, this is actually force balance what happens there, and then there is a moment balance. In other words, if you want to rotate the aircraft, then you essentially need axis frame about which you need to rotate, and that is where there is a concept of body axis frame, which is centered at the center of gravity of the airplane, and the x axis just points towards the front, and y axis to the right side, z axis to the down, all that we have discussed before. And any positive motion about the x axis like right hand thumb rule sort of thing, and that will call positive roll actually. So, similarly, if you grab this y axis by right hand and then your thumb pointing towards the y axis, then the direction in which the aircraft will rotate is actually called pitching motion actually. And similarly, this is rowing motion. So, roll, pitch, yaw are about the motions about the x, y, z axis actually. And this is what we discussed before. This is this type of motion is called roll, and primarily these black surfaces that you see here, these are ailerons, they will contribute towards this, and they are they are deflected not symmetrically but asymmetrically. That means one is up, another one will be down. So, that the differential force acting on the side of one side of the wing over the other creates a kind of a moment there, and for which this aircraft kind of rolls actually. Similarly, it is when you do this symmetric deflection of the elevator, it creates a moment about the CG in this direction. Essentially, it leads to pitching action. Okay. and then similarly it is like if you create that deflection of rudder, then it essentially causes the yawing motion actually. So, all these things we have seen before. Now, the question is in an automatic flight control system, we have to generate all these control surface deflections properly, either directly coming from pilot command or even coming from a guidance loop actually. That means autonomous flight and all that. If the guidance thing is also in action, then the reference command to follow and all that comes from there, and all these control surface reflections we have to create appropriately actually. That is the problem of so called control system design for aircraft or autopilot design actually. Okay. While doing that, we have also derived this what is called 6 degree of freedom model of the aircraft. We have seen each of the variables we have discussed before. These are UVW, that body axis component, velocity components, and then the PQR are the roll rates, pitch rates and yaw rates about the body XYZ component. These are Euler angles phi theta psi, and these are like XYZ as seen from the inertial frame possibly situated on the ground actually. So, this will give the coordinate the coordinates of the CG of the vehicle as it moves as seen from the inertial frame that way. And then there is a h dot. H dot is actually essentially negative of Zi dot actually. If Zi is here, the negative of that is height gain actually that way. Okay. So, anyway, so these are the what is called 6 degree of freedom model, and then we discussed about linearized models. Okay, that means this is like too many variables and two coupled equations and all that, especially when you expand these force moments which are coming from aerodynamics, x, y, z coming from aerodynamics things, and x t, y t, z t coming from thrust components, and similarly LMN and LT, NT, I mean these are all moment components coming from thrust, and these are aerodynamic components acting on the body axis. Once you expand these coefficients and all that, it takes a very complicated form and becomes difficult to analyze as it is actually. So, what the next idea is, we have decoupled this motion along what is called longitudinal dynamics and then lateral dynamics actually. So, when you do longitudinal dynamics, you consider these perturbed motions that u, w, q and theta, you club them together. That is one side of the thing, and in the lateral mode you do that in the reverse. I mean this delta v, p, r and delta phi basically. So, these 4 variables and the other 4 variables you club together sort of thing actually. Okay, so, you kind of decouple these variables from the other side, because in principle all the variables are coupled with each other, but there are some strong dependency and weak dependency actually. So, you club them together in a strong dependency sense and tell this is what is my linearized dynamics looks like. So, essentially I have a state space form x dot equal to x plus bu, where a b takes this form, x is the definition like that, and u c is the control vector which is essentially delta e and delta t. Okay, that is elevator and thrust deflection angle actually, thrust deflection percentage here. So, once I have this dynamics, these definitions and all are like aerodynamic derivatives and all are defined that way. Once I have this state space model, then I can proceed with the state space design, or I have a liberty of even going to the transfer function approach and then talk about some sort of a transfer function analysis and all that. So, this dynamics, these 4 state variables, we still decouple that into 2 to each, and then this is like what we discussed as short period mode, which is typically the aircraft vibrates quickly and it subsides actually. It does not go through a long, the entire vehicle does not go up and down, it is just a vehicle motion about its own CG actually roughly, and that will lead to a small perturbation of the vehicle trajectory a little bit actually. So, that is essentially pictorially depicted like this, like you have this change of angle of attack, but it will die down very quickly. Okay, so, immediately you will have some vibration and then it will go actually. So, that is heavily damped. A short time period, and while it does that, it does not really lose its velocity actually. Okay, so that is the motion that you are talking about, and this motion is typically given by these 2 equations alpha and q actually. So, essentially delta alpha dot and delta q dot, they are given like this linear equation. Okay. And if you really want to have a state space this model getting converted to transfer function thing, then we know how to do that. So, if it is x dot equal to x plus bu, then we know, okay, this is if given like x dot equal to ax plus bu, okay, and obviously y equal to, let us say, Cx, that has to be taken care. Then y of s divided by that u of s is nothing but this C Si minus A inverse B, okay, right, C Si minus A inverse into B actually, plus D, but D is not there here. So, that is implicit actually. So, if you do this, then you will get a transfer function actually. So, that is what is done here, and then you get this delta alpha by delta E transfer function that way, and delta q by delta E transfer function that way. Typically, these are second order transfer functions, and that is also evident from this second order state space model actually. Because normally this is another reason why you wanted to get back from 4 dimensional to say like 2 dimension, because essentially you will end up with second order transfer function for using which we can do the design very easily rather compared to a 4th order polynomial and all that. So, that is what it is done here. Then long period actually is a reverse way of doing that. I mean, looking at the thing is not very short period oscillation and all, it essentially the entire vehicle goes up and down like that in a relatively longer time actually. Essentially this there is exchange of kinetic energy and potential energy. The entire vehicle goes up, then slowly comes down, then again goes up, then comes down like that. So, in that process it changes the pitch, attitude, altitude and velocity, okay, and all this happens with some sort of a constant angle of attack actually. Angle of attack does not change. Remember, angle of attack is the angle between attitude of the vehicle with respect to the free stream velocity actually. So, that remains kind of fixed actually here. So, if you want to approximate this figured dynamics or long period dynamics, then this is the way to do that. Delta u and delta theta you try to club together, okay, then this is the transfer function that you are taking, and here this delta t, that is the engine deflection engine or thrust level percentage, it actually plays a role also actually here. So, this is elevator deflection angle, differential angle of course. This is differential thrust magnitude as seen as like a percentage of maximum thrust actually that way. So, once again if you, but these are, remember these are 2 control actions, okay, and this one is very fast and compared to this delta t. So, you can assume that delta t remains 0, okay, if you assume 0 then it becomes like single control input again, and you can again come up with this transfer functions for both delta u with respect to delta E and delta theta with respect to delta E also actually. Again these are second order transfer functions. This is all about longitudinal dynamics. What about lateral dynamics? Again we can do the almost the similar way. We club this V, P, R and phi together, all in the sense of small angle, small perturbation actually, and then we discuss about this linear or rather linearized system equation, and where this control is actually 2 controls now, and both are of similar time scale. Both are fast and both have their equal impact. So, we cannot take away one, or we cannot assume that one is 0 and all that actually. So, we have to live with that. And then this particular motion, this analysis of this particular thing leads to several phenomena, and one of that is directional divergence. That means it does not possess directional stability. So, we will have this side slip angle keeps on building. So, it goes to slowly, it will deviate from its intended path, and that is called directional divergence actually. And then you have spiral divergence. That means if it is a gradual spiraling motion and also, in other words, the angle of attack keeps building very fast, as well as it is not just a side slip angle, aircraft also rolls actually, okay. So, it kind of goes through the spiral divergence in a fast way actually. So, this is a slow divergence, it will keep on going slowly. So, aircraft does not turn, but because of the side slip angle it just keeps on going away, but here the aircraft also turns actually, also rolls and all that actually, okay. So, this gives you large this large spiraling motion and all that. Typically, this motion, the directional divergence is controlled by rudder, whereas the spiraling divergence is controlled by ailerons. Ailerons will typically produce much more moment actually, because Ix, even though because the inertia about x axis is small. So, the ailerons in moment is with respect to x axis moment of inertia. So, moment of inertia about x axis is small because mass distribution along x axis is typically small actually. I mean the distance of mass distribution from the x axis is typically small, and hence the I x axis is typically small actually. That is why these ailerons will have larger impact on the aircraft actually that way. Okay, so and then there is an interesting phenomena which couples both of that, and that is something called Dutch roll oscillation. That means it coupled directional and spiral oscillation both sort of thing. So it will first it will turn towards the left. I mean it will roll towards the left. So it will also diverge. So it will go towards that. By that time it turns to the right. It will again come that side and then go that way. Typically it is like how these Dutch people play skating on the ice and all that that way. So that is why it is called Dutch roll oscillations, and it is typically controlled by using both aileron as well as rudder actually. So together they have to be applied actually. So if you really want to have Dutch roll dynamic capture, I mean this transfer function approach and all that, this is how typically it I mean the state space equation takes the form. And remember this is like every input every input in the sense both aileron as well as rudder will have impact on both the variables actually. So if you want to visualize what is happening, then for each input to each output, then you have to construct these corresponding transfer functions with respect to that. So we have this delta beta over delta A and delta beta over delta R as well. Similarly, delta R over delta A and delta R over delta R. So all these things are like second order transfer functions actually. Okay. And using that you can try to design your control system actually. If you rely on classical control system, typically you need the single output single input models actually based on transfer function, and that is what you use actually. So that is like a quick overview of what we have already done before. I mean this we have derived Sixtov equation, we have derived linearized equation, we have discussed about this lateral instability, longitudinal instability, I mean this short period and long period and Dutch roll all sort of things. This was just a quick overview. Okay. Now coming to the flight control system overview. Okay. What happens there is typically if you put all together, this is what happens in a flight control application actually. So aircrafts typically have a number of sensors. Okay, they have this inertial navigation unit which consists of gyros and accelerometers, all sort of things. They will also have this air data system, magnetometer, all sort of things actually. Many sensors. I will list them out in a next slide or things like that. So this sensor information will keep on coming to the flight control computer, and each aircraft carries a good flight control computer basically. Okay. And commercial aircrafts do carry backup computers as well. Right. So that information keeps coming, and what the aircraft pilot wants to do, and he can do a variety of commands actually. He can give flight path command, he can give velocity command, altitude command, all sort of things, and those information are also fed to that. And then this flight control computer takes the help of flight dynamics into picture, like its own moment of inertia, mass, all sort of parameters actually, aerodynamic modeling, things like that. And then by appropriate computing computation of the control command, it issues the command to the actuators basically. So these actuators will essentially deflect all these throttle position, rudder position, elevator position, all sort of things, and that is how the entire aircraft control surface control system is activated actually. So that is all what happens in a typical flight control system. Now the question here is this driving a very rough car which does not have any automatic control support, and then driving that for a long duration is obviously straining actually. So it cannot be done, and in a high risk game like an aircraft flying and all that things like that, we need certainly some support of automatic control system for the pilot actually. Otherwise, imagine a case where a commercial aircraft pilot will keep on flying for let us say 10 hours, 12 hours, 14 hours. From beginning to end, he has to be consistently giving input command to the aircraft. This is not feasible actually. Okay. So that is why we talk about augmenting this as much as possible, augmenting this control system as much as possible with automatic control laws, so that the pilot can relax on the way actually. Many of the things can be done in an automatic sense actually. Okay. So that is what autopilot systems all about actually. So as I told, sensors, these aircrafts can typically take a lot of sensors, and one sensor is altimeter, which essentially gives height above the sea level, and then they have air data system which gives a host of information like airspeed, angle of attack, Mach number, air temperature, all sort of things it gives. Then the magnetometer sometimes, which gives you heading angle compared to the, remember magnets are typically aligned with respect to north south. So, if your base is aligned somewhere else, then it will give you some sort of angle, which is nothing but heading angle, how it is, how the aircraft is oriented with respect to north south direction actually. So, that is heading angle it will give. Inertial navigation system, it is a big system of course, it consists of accelerometers and gyroscopes, and these gyroscopes for example can be position gyro, rate gyro, like that, depending on the application what you are talking here. And then they are also supported by something called global positioning system nowadays, which are essentially satellite based navigation aids and all that actually. Okay. So, they have their own positive negative issues here. I mean, for example, INS is a self contained unit, it does not need external support. Once you initialize it properly, okay, and then it acts on the Newton's law actually. So, if your initial conditions are proper, then you can integrate this mx double dot equal to f, and then x double dot is f by m, all sort of things. Then once you know this x double dot information, integrate that, you get x dot, and integrate one more time you get x, provided you know the initial conditions properly. And similarly with respect to gyroscope, you have the rotational dynamics into picture. So, I theta double dot is torque and all that. So, integrate the theta double dot equation essentially. So, if your initial information is really good, then it does not lead to too much of accuracy issues, but they have their own sensing units and all that. So, they have their own filters in the loop, and it is a complex unit essentially, and nevertheless it does not require any additional external support actually. Okay. So, depending on the level of sophistication, it can give you very good information actually. Okay. But as the duration goes high and all that, they have this problem of drifting, they have the constant bias acting on that, integration of that leads to large error, like that actually. So, many issues are there. So, now people talk about position fixing. So, there is like a 24 satellite constellation and all that, you select those 4 satellites, and based on which you kind of find your own position. By kind of computing some unknown variables with some geometric constraints and all that. So, if you do that, then it essentially leads to very accurate position, and also gives you what is your ground speed with respect to ground actually. Okay, remember air speed is coming from here, air speed is speed with respect to air, but air can have some relative velocity with respect to ground. So, this ground speed can be measured directly using GPS. Another constraint is like GPS can be very accurate, but the frequency of update cannot be very fast. So, it is relatively much slower than INS system. Okay. So, now people talk about can you really fuse these two systems, that means INS GPS fusion and all that actually. So, you will get a lot more information around that actually that way. Anyway, so these are a host of sensors acting on the flight vehicle, essentially a good commercial aircraft. And then many of the transfer functions can like many of the transfer function for most of the sensors can be approximated simply by a gain actually. Remember, each of the sensors are dynamic systems by itself. They sense not immediately instantaneously, but they have their own sensing mechanism which essentially excites the internal system and things like that. But the point here is their settling time is very fast compared to the settling time of the aircraft itself. So, anytime you want an information, the information is typically there actually. So, that way. So, that means most of the transfer functions can be just approximated with a gain instead of a dynamic system actually. Now, how about actuators? I mean, that is ultimately what will excite the control systems, and these actuators consist of variety of things. One is electrical actuators, other one is hydraulic actuator. Sometimes pneumatics are also used, and typically these are first order systems, whereas electrical actuators are typically second order systems in general. But they can also be approximated as a first order system with a small angle displacements and all that. If you really do not demand too much of deflection like fin deflections from the system, then there is no need to kind of approximate that with second order thing. You can very well go with the first order system as well actually. And then there are ideas like you can combine these actuator benefits and all. You can talk about like electromechanical actuator and things like that. So, electro-hydraulic actuator, I mean there are like combinations of that actually. So, these will play a role in the automatic control system design actually for the entire vehicle. Now, applications of automatic flight control system, how do we kind of design this automatic system for the aircraft? They can talk about variety of things. And first thing that comes to mind is cruise control system. That means, once the pilot takes the aircraft to certain altitude, sets the direction and things like that, for a large duration, I mean it has to just continue flying like that, and that is what is called cruise control, and in that is the segment where pilot needs to be really relaxed actually. So, that means that is the segment we design variety of cruise control systems, and one thing is what is called attitude hold. That means the angular positions of the vehicle and all, so can be hold like that. Okay. So, that is called attitude hold. Essentially this is to maintain the pitch roll and heading angles actually. So, any dispersion of those angles needs to be nullified. Okay. Suppose you want certain pitch angle, certain roll angle and things like that, let us hold it actually. That is the easiest thing that you can visualize actually. Next comes to mind is altitude hold. That means you really need to maintain a certain height actually. Okay. So, that is these are all regulatory systems, remember that. That means there is some value I want, any perturbation around that I want to nullify actually. That is the kind of problem that you are talking here actually. And then there is a speed control mechanism, and this one has come to cars also by the way. Okay. So, speed control is essentially to maintain a constant speed or Mach number irrespective of whatever local phenomenon of let us say change of angle of attack or change of like a drag value and things like that. Then you can the automatic speed control mechanism comes to picture, and either it increases the power of the engine or decreases the power of the engine. So that the ultimately the speed is maintained actually. And that essentially has come to cars actually. Lot of commercial cars have speed control. Essentially they call it as cruise control actually. They also call it as cruise control. So, it nothing but it just simply maintains the speed no matter whether you are climbing a hill or you are going down the hill or you are going on the plain highway basically, either way. Okay. And obviously for safety purpose and all, the cruise control is cancelled once you put a manual brake and things like that, because after that your car should not be again speeding up and things like that. But again once you take out the brake and you see okay nobody is there on the path for kilometers away and things like that, you can excite the speed control again, this cruise control for the speed again, and again you do not really need to kind of control the speed of the vehicle manually by changing the petrol pedal or accelerator actually. So, very same concept is there in the aircraft, and essentially the idea started from the aircraft by the way, that way. Alright, so next level is what is called stability augmentation system. Okay, this is essentially cruise control system, will fall under variety of other things also. This is just one thing, altitude hold, attitude hold, speed control hold, all that. The other thing is what is called stability augmentation system. Okay. This stability augmentation system is essentially done for two reasons. One is first of all stability enhancement. That means let us say your aircraft is very marginally stable or it is really unstable, like let us say fighter aircraft and things like that. Then many times you want to make the aircraft behave as if it is a stable vehicle under the influence of continuous controller actually. If the control system is actively taking part, it is actively excited, then under that the part of the system behaves as if it is a stable system actually, and over that stable system you can still excite the system with further input. I mean that is also there. But in general this stability augmentation system means that you compute some sort of a component of the control along with which the plant will behave as if it is a stable plant actually. Okay. So, that is the first thing. And normally the second thing which is related to the first one is something called handling quality. Handling quality is like the ease of driving a car. You can visualize it that way. So, that is like suppose you want to drive a car, you feel okay this car is easy to kind of drive, another one is not and things like that. There are variety of reasons. The thing is if it is too responsive, it is not a good car. If it is very sluggish, it does not respond well, then also it is not a good car. So, you have to have some sort of a good response coming from that, and that is what is the concept. That kind of ideas are called handling quality in aircraft. How the pilot can handle the aircraft in a good way. In other words, he really wants to go up and he wants to give a command of let us say change the altitude from altitude 1 to 2, then the aircraft should really change it within that much time actually. And if he visualizes let us say let me pitch up the nose and things like that, the aircraft should pitch up and it should kind of quickly pitch up rather actually. Okay, without too much of oscillatory, too much of overshooting, things like that actually. So, those qualities are called handling qualities. and stability enhancement and handling quality are roughly kind of coupled with each other actually. Okay, that is one thing. The next level of automatic flight control system is something called like landing aids, for example. So, when you really want to land an aircraft, that is the most crucial part of an aircraft flying, by the way, and that is the most dangerous part also in the entire flight segment actually. So, that is where we need lot of aiding instruments and things like that actually. So, first thing that comes to mind is alignment control there. So, aircraft can come close to the city or close to the airport, but first it needs to align properly with respect to the runway. Remember, runway width is not very much. If your alignment is just not proper, you have some angle offset and all that, the aircraft can run away from the runway actually sideways. So, that angle alignment has to be tightly controlled actually, number one. Number two is it needs to have some sort of a glide slope control, that means it has to continuously decrease its altitude from its cruise condition to the almost 0 height with respect to airport runway height. Okay. And then it is also something called flare control. I will touch upon a little bit as we go along, but roughly speaking this after alignment happens, suppose this is runway, let us say, okay, this is runway, then the aircraft should come roughly in a straight line, that is called glide slope, and then it should flare up, in the sense that after that it cannot just go in a straight line, and if it goes, then it will hit the ground in a very bad way. So, what is done is after once the aircraft is very close to the runway, they excite some sort of a exponential path actually. Okay. So, that while it touches the runway really, and the vertical component of the velocity is manageable actually. So, this part is called flare and this part is called glide slope actually. This is flare, okay, and this is glide slope. And before that it has to align actually. So, that is also like alignment actually. Okay. So, this is like alignment, glide slope and flow, that is where your control system also comes into picture actually. And in a reverse way it is also, you can visualize that automatic takeoff also has a reverse sequence basically. So, that is when you talk about landing, automatic takeoff is also kind of included in that actually. So, there are various levels of automation that we can visualize as far as application of automatic control system for flight control applications are concerned. The most popular is of course cruise control, which is a regulatory mechanism, and then these are the design side of the story. I mean, this is what happens as the aircraft flies in each of the flying condition, and this is happens without pilot's knowledge probably. Other than the fact that maybe test pilot will know that or something, but regular pilot may not even know that. Okay. So, that is going inside the flight computer in a built in manner actually, and landing aids are anyway there, and takeoff aids are also part of the deal actually. And there are secondary level flight control applications which are not talking here, and these are like path design, guidance design essentially, where the aircraft will go, what direction it will go, what time it will reach and things like that actually. So, that is guidance level, which is outer loop control sort of thing. That is also a control loop, and if you want to use control theory for that, you can very well use it actually. And in missile guidance application it is used heavily anyway. So, similar concepts are there for aircrafts also actually. But that means the mission of the aircraft also becomes autonomous actually. Okay. And that concept is very popular in UAV domain, where the pilot is not there, it is unmanned aerial vehicle. So, it needs to be guided in an automatic sense actually. Okay. In that sense it comes very close to missile guidance actually. Alright, so there are various levels that we discuss here, and then this is like, okay, that as far as techniques that we have studied route locus, body plots, liquid plots, PID design, and time domain techniques. We have studied pole placement, eigenstructure we did not study, and but optimal control like LQR design we have studied and things like that. So, all these techniques can become quite handy for addressing those issues that we discussed actually. Now, for the rest of the class I will give you some examples, and some particular, we will not talk each and every system around that, we will just take you through a couple of situations and couple of examples like that, which will give you some sort of a good feeling of what is going on actually. Okay. So, let us see, I mean this frequency domain design approach, that is what I am talking here. And remember, this is while you talk here, the frequency domain means we will largely confine ourselves to this, and I will take the help of route locus and to some extent PID design concept actually. Bode and Nyquist are analysis techniques, and I think they are also useful. We are not going to discuss here. And here we will discuss like some attitude control and then speed control, things like that actually. Okay. And next class probably we will go through this some of these time domain techniques, and then we will follow it up with the concept of gain scheduling and things like that way. Anyway, so we will this is where we are, and some techniques we know, some problems are at hand, and so we want to kind of fuse them together. We want to apply those techniques for these problems actually. Okay. So, let us see that, and the first thing that comes to mind is velocity hold control system. So, this is that speed control system basically. So, I mean anyway, this entire class material is taken from this this book. It is a nice book as far as automatic control application for flight control is concerned. It is R.C. Nelson from McGraw-Hill and 1989, but I think there is a newer version also available. Okay. So, if you want, you can buy the book also. It is a good book actually to buy. Anyway, so this is like velocity hold control system. What do you do? Obviously, in any type of control system, and these are all based on this PID ideas and things like that. So, you have some sort of a reference command, okay, that means that is that much speed you want to maintain, and your actual speed can be something different. So, you give the throttle command as a kind of some constant gain times the error in the output actually. That is the P part, that if you really want to talk about PID control, then P control is like K times E basically, or minus K times E, whatever, depending on that. So, you have the output there, and you know that this output that you are talking, this delta U, that means the error in the speed, is actually a function of this error in this reference command and things like that, which is typically compensated by engine control, engine throttle control ultimately. Okay. So, here we have to have this error signal known to us first, and for knowing the error signal, we need to know what is my current U and what is my reference U. Okay. Typically, this is actually okay. If you put delta U is deviation and things like that, that is 0. Delta U, I mean desired delta U is typically 0. Delta U is the difference of speed basically, reference speed. So, anyway, so you have this actual information which you can sense it using this let us say air data system or GPS system and things like that. So, depending on whatever is your required value, you generate a kind of an error command, and then you multiply that with some gain, or if necessary you kind of derive this rate so that you can talk about PD control, or do this integral manipulation here. So, we can talk about PID control, things like that, and ultimately this command will go to that, and then it will pass through this engine lag also. This is what we can visualize that as an actuator system actually. Okay. Pass through the engine lag, and ultimately that will excite the system actually. So, as long as this error is there, okay, and then this engine throttle control is excited actually. Okay. And that way it will take it I mean it will keep on getting excited until it is kind of 0, and the correction happens in the proper direction actually with this negative feedback in the loop actually that way. Okay. So, this is how this is mechanized, and once you know each of the subsystem transfer function, gain values, things like that, there will be some sort of a gain tuning mechanism for this engine control, throttle control actually. So, those gain tuning you can tune based on time domain specification, based on like let us say damping specification and things like that. There are a variety of specifications that you can talk about, and based on that you can tune these gains and then visualize or kind of realize this control system actually. So, that is essentially the idea of velocity hold control system. Now, coming to attitude control system, okay. What you do here is very similar anyway. So, instead of velocity, you kind of sense the real attitude, either pitch angle theta or roll angle phi or kind of yaw angle psi, either way. And then depending on what is your kind of intention, so you take the corresponding error signal, either E theta, E phi or E psi. Okay. So, you and then excite the servo control mechanism to get a value for this deltas actually, either delta elevator deflection or kind of rudder deflection or aileron deflection, things like that actually. Okay. This will be elevator deflection, this is aileron deflection, and this is rudder deflection. So, this is typically small typo mistake probably. This is aileron deflection delta A. Okay. All right. So, that is how it is actually. So, essentially what you are doing, you are sensing the angular position, whatever position there. Then there is a desired angular position, let us say the pilot wants to pitch up. So, that means he is given little bit theta command increase and things like that, or he wants to roll. So, he is given phi c command and things like that. Okay. So, that way this command is actually compared with this actual command which is coming from the sensor, I mean whatever sensor you employ, and then based on this error signal you excite this control mechanism, largely done through PID control anyway. So, then generate this actuator commands actually. Okay. Then it will pass through this actuator system, and what you see servo control and all is like actuators also in the loop actually that way. Okay. So, ultimately this will be kind of coming out of the actuator actually, output of the actuator, and it goes to the aircraft and excite the system actually. So, that way. So, it is not very much different from what you have studied in feedback control actually. You have something like a set point regulation problem, you have got some command, there is actual command and there is some sort of a error signal, okay, and then based on this error signal if I was just multiply with a gain, then I got P control. If I do this algebraic manipulation of like let us say differential or differentiation or integration and things like that, then I can realize a PID controller actually. Okay. So, that is how it operates. Now, let us instead of philosophy, let us talk little more detail of what is called roll attitude autopilot. Okay. And similarly, you can talk about let us say pitch attitude and yaw attitude as well. So, I will pick up a roll attitude autopilot and try to let us say explain what all things goes there through an example probably. So, if you really see the roll attitude autopilot, this is the mechanism. You have got some sort of a roll command coming from let us say pilot, and there is attitude gyro which will sense the phi actually the real phi. So, obviously, you have an error signal and it has to pass through certain control design to get this delta A basically. Okay. So, this delta A is aileron deflection that will be given to the roll dynamics, and I mean that will pass through the system model that you are talking about actually. Okay. All right. Now, the components of this, as you see it here in the block diagram, we have a model for the roll dynamics which is kind of important here. Based on that model we do several things, we can analyze the things, okay, and we can tune the gains actually. This gain tuning will depend on this transfer function what you have actually there, because closed loop transfer function will be like this transfer function into that transfer function. So, obviously, this transfer function plays a role while tuning the gains actually. Okay. And obviously, we need attitude gyro to find out what is our actual phi, and we need a comparator thing to realize this comparison signal like plus minus and all that, we get a error signal, and obviously, we need an aileron actuator to finally execute the command actually. Okay. So, these are all the various components that will go through the roll attitude autopilot, and similar thing will happen for pitch attitude as well as yaw attitude actually. Okay. Now, with this let us say you pick up some sort of a problem here. Now, okay, these are all parameters of the aircraft and all that, where it goes and all, it will go to that modeling part of it, will not concentrate so much on that right now. We just assume that these numbers will go somewhere in the model actually that way, somewhere in the transfer function. Okay. So, what you are telling here is the aircraft has these characteristics, okay, and our job is to design a roll attitude control system to maintain a wings level attitude, that means phi has to be 0 basically, okay, and for the vehicle has this kind of thing actually. And then not only that, while assuring this kind of this wings level conditions and all from any initial condition, suppose the aircraft is already rolled, you want to make it wings level, that is the problem actually. And while doing that, we want to assure that this damping ratio remains at 0.7, 0.707, and the natural frequency happens to be 10 radian per second. I mean, that is the desired bandwidth specification and all that actually. So, you have a damping ratio for that, and you have omega n that actually on the closed loop system. Okay. So, can we do that? I mean, that is what is the problem, and you can assume that the aileron actuator and the sensor gyro can be represented by some sort of a constant gains only. So, they do not have this transfer functions coming into picture, additional transfer function. We assume that these are simply gains actually. Okay. So, can we design a control system to do the job actually. Okay. This is what you can do. Now, if you see this delta phi to delta a, this transfer function that we are talking here, okay, and this takes the form of this one. So that means this is like a second order pole. The two poles are there, and there is numerator there is no 0 actually. Okay, so it is only a two pole system actually. Okay, so forward path transfer function. If you see this transfer function, this is nothing but this to this transfer function. Okay, delta a to E phi. This is E phi probably. Okay. You can put that maybe this is E phi, okay, delta a to E phi, okay, and multiplied with that fellow delta phi to delta a. This is like that, right, this to that transfer function delta a to delta E phi, and then delta phi to delta a basically. So, that transfer function. So, if you multiply these two transfer function, you will get it actually. And we are assuming that the Ks is 1. So, we essentially end up with unity feedback kind of situation, where the analysis becomes easier. Any other gain is also fine actually that way. Now, the open loop transfer function, if you see, this is G of s is known to us, H of s is known to us. So, Gs times Hs is nothing but that actually. So, Hs being 1 is nothing but simply G of s. Okay. Now, these two gains I can multiply together and I can define something called K actually. Okay. If I define these two multiplication K times L delta A is nothing but K, then my open loop transfer function takes the form something like K by S into S plus 0.5 actually. So, obviously, you have a pole at 0, I mean 0 location 0 0, and you have a pole at minus 0.5 0 actually. Okay. So, let us draw the root locus diagram now, and if you do the root locus diagram, so this is one pole here and one pole here. Okay. This is one pole in the origin, okay, and one pole here, some this minus 0.5 location. So, the poles, I mean if you apply the rules of the root locus or you simply draw it using MATLAB and things like that, they will start from the pole, they will go that way, and then ultimately they will meet here and then they will diverge this way, right. I mean that is the pole actually. Okay. So, now once you have this kind of a root locus, you have to find out gains from there, okay, which gain will satisfy wherever you want to operate. Now, I remember that one of the problem thing I mean what demands is that zeta has to be 0.707. Now, zeta is nothing but cos theta of where theta is this angle actually. So, cos theta is that 45 degree, remember 0.707 is like 1 over root 2 sort of thing, and 1 over root 2 cos 45 is 1 over root 2. That means, if I draw a 45 degree line, whatever line is that, and wherever my root locus crosses through, I have to select a gain for that actually that way. Okay. Now, if I select a gain, that means I have to select a gain which is which corresponds to this location really. Okay. This is what I need to select actually. Okay. Now, this gain can be found out from, because this lies on the root locus, obviously it satisfies the gain condition sort of thing, I mean the magnitude condition. That means, if I take magnitude of the root locus, it has to be, I mean the open loop transfer function, it has to satisfy 1 actually. Okay. Open loop transfer function is this. So, if I simply take magnitude of that, it will satisfy 1 actually. So, that is why I do that, and essentially it leads to like what value of this when that k and all that, it leads to this thing actually. Okay. Because that point you know the s value at that point is known to us. So, you substitute that and then find out the gain value actually. So, gain turns out to be like that. Now, the problem with this, so that means by selecting this gain k, and k is essentially this, that means we are able to select a k a, because we know this parameter L into delta a and all that, this is this is part of this transfer function. So, once you know this into that is that value, so obviously you divide by that value to get k a value. Okay, so that is how it will operate there. But once you know the k a value, that is not sufficient, and in the sense it satisfies this zeta condition, because we have selected that way. But what about omega n condition? And omega n in this particular case, if you go back and compute, then it turns out it is nothing but 0.35 radian per second, way less than the desired value of 10 radian per second. That is what we wanted. So, this cannot simply by gain tuning we cannot do the job, that is the thing actually, that is the message. One thing can be achieved, not both actually. So, now how do you do both? And that is where this stability augmentation system comes to picture, and that is okay. Observe this condition now. Let us say we somehow extend this line actually. Okay. Now, at some point of time, so remember this is nothing but omega. The magnitude of this length gives us omega n actually. That means, if I keep on moving along that direction, obviously my zeta remains constant because angle remains constant, and some point I will get the z omega n actually. Okay. So, this point happens to be that is z omega n. Now, the problem is the root locus has to pass through that. Now, if the root locus has to pass through that, then this pole location P 1 what was earlier at minus 0.5 has to be shifted to point P 2, somewhere still left I mean further left to this P 1 actually. But this location of poles P 1 is coming from the transfer function of the aircraft dynamics, which you do not have a direct hold on actually. Really, if you want to put the pole there, then the only way to do that is go back to the design stage and have a larger wingspan actually. Like, but that is not an option for the I mean aircraft has already been designed, and our job is to do the control system loop in that. Can we do the thing by augmenting the system in an artificial with an artificial control system actually? That is the problem there. So, that is what is written here. Moving the pole P 1 to P 2 is impractical unless there is a increase in wingspan of the aircraft. So, that is not an option with us, and hence the cure is to have a stability augmentation system actually. So, we augment the stability so that it will see the omega n that we require actually. Okay. Ultimately, the closed loop root locus has to pass through this point, or otherwise there is no, I mean no hope at all. This point is the point which will give us the value of zeta and omega n both actually. So, closed loop pole closed loop root locus has to, I mean the root locus of the closed loop plant has to pass through that anyway. Okay. So, that way it has to be decided on that, I mean the anyway. So, that is we will see that and how do you do this actually. So, what you do here is, instead of simply having this kind of a realization, what you see here direct realization with simply an actuator gain I mean K sort of thing. Now, you have some sort of a 2 loop transformer, I mean 2 loop some sort of a realization here, where that okay, not only I will give theta feedback, that is what I was doing here, only I was giving some only angle feedback. Okay. So, instead of that I will give something like a, I do not know, this is not theta, it is phi actually. Okay. Instead of giving only phi feedback, I will give some sort of a phi dot feedback. Phi dot is tightly coupled with P anyway. Phi dot is P plus some small components and all that. So, I take P which is roll rate now, this is roll angle and all that. So, this roll rate feedback I have to sense now. So, that means I can do that only using a rate gyro, not position gyro only. So, let me sense that with a rate gyro, and then that information I will get it, I will find out that I mean this particular loop I will close it first. Okay. So, if I close this loop first, with respect to this loop, if I put a big box out here, then this outer loop is still there. The outer loop is what we discussed here already basically. Now, this particular loop I want to put one more loop which will kind of give me the desired properties that I want actually, that we call as inner loop actually, IL. Okay. So, this inner loop transfer function and things like that. Now, if you do this this inner loop transfer function can be expressed as something like this, delta P to delta A. So, that is given like a first order system actually. Okay. So, once you have that kind of a thing, then that transfer function of the inner loop becomes like that for this example, let us say, and ultimately you can see that this is the transfer function of the kind of inner loop and things like that actually. Okay. So, what happens now? If you see this closed loop transfer function for the inner loop and all, it is no more this just plus 0.5, you do not have to live with that. There is a gain fellow which is coming here, and this gain can now be selected according to our wish actually, okay, because that is on our hand now. Okay. So, we select a gain in such a way that the poles are shifted far away actually, whatever we wanted here, this pole has to be shifted that way and all that. So, that one we can do by selecting a gain here actually. Okay. So, that because remember S into this 0.5 location was coming from this factor only. Now, this is not 0.5 plus something, that means S value is minus 0.5 minus KIL actually. So, it will go now minus 0.5 minus KIL that way, it will get shifted that way actually. Okay. So, that means this closed loop pole and I mean this root locus and all for this augmented system, root locus for this augmented system will not be like this dotted line, now it will be that dotted line basically. So, that way you can select an appropriate gain which will correspond to this value of the root locus actually. Okay. Alright, so that is how it is done. So you have constructed some sort of inner loop system by doing some sort of a rate feedback, okay, which has altered this loop, I mean loop behavior. Okay, previously it was nothing. This loop was open actually. It was there, but the feedback loop was open. So once you put a feedback path, this entire system behavior is something different actually. So that is the property that is helping you for shifting this pole location P1 to P2 actually. That is how you will be able to do the job. Now if you just see that it satisfies all the properties, there is a nice behavior, it settles quickly, there is a less percentage overshoot and things like that. So that means both fast response as well as less percentage overshoot and all that can be achieved actually. So, but for that you need to have a stability augmentation system, and along with that you have to have a regular control mechanism, regular feedback of the position actually. Position feedback is essential as well as at rate feedback is also essential that way. So, stability augmentation in general does this kind of a thing. Inherent stability of an airplane depends on aerodynamic stability derivatives, which you do not have too much control on that anyway. Okay, then magnitude of the derivatives affects both damping and frequency of both longitudinal and lateral motion, that is all facts actually. Okay. So, and also remember the derivatives are functions of flying characteristics which change due to the during the entire flight term, they do not remain constant also. Okay. They keep on changing, because remember aerodynamic coefficients are typically functions of Mach number, functions of dynamic pressure, functions of alpha and things like that actually. Okay. So, they keep on changing anyway. Now, what will happen is what we are doing here is the control system which will provide this artificial stability to an airplane having undesirable flying characteristics are commonly called as stability augmented system. So, that means part of the control is built in basically, and then another part you excite through different one actually. Okay, so, that is what is the idea of stability augmented system. So, we give let us say another example before we wind up. Let us say short period dynamics is something like this. Okay. Where let us say this dynamics has poor short period dynamics and we want to augment that and then get a better short period dynamics. How do you do that? So, numerical values if you substitute, let us say it is having something like that, and this value being very small, remember this is like 2 zeta omega and all that actually, this is that much. So, zeta is very small. So, it almost has no damping actually, that some oscillation happens, then it will keep on oscillating, obviously we do not want that. So, we want to have faster decay and things like that. So, then what you do, okay, let us say delta E, this is your actual command, right, that is what is coming from the pilot. This delta E we decompose that as one is pilot input directly, the other one is some artificial command which is like k theta dot actually. Once you put that in there, then you put k theta dot directly here. So, this entire term part of that goes this side actually. Now, there is a k theta dot component and here is a theta dot component. So, that gets combined, and hence you will get some sort of a closed loop dynamics like that. That means 2 zeta omega n is not only this one, but it is this one plus this one now, which is a larger number. So, we can have some sort of a if you saw omega n square is that much, still that is there. So, that means zeta value is quite high now actually, and by varying k value, this is your tuning parameter here. Okay, if you vary k value, that means various components, how much you want to kind of artificially give input. The moment pilot gives an input, your any additional input is automatically generated. Now, how much of that you generate is a tuning quantity actually. So, by doing that you can augment this zeta, you can manipulate this zeta, and that will essentially lead to desired damping actually. So, that is, these are all stability augmentation system. So, then as I told, other applications will include landing system, which is like alignment control, glide slab, flare control, we have discussed all that, and more details you can find on the book. Probably I do not have too much time to discuss on all these details and things like that actually. So, with this exposure we will probably stop here. Thanks for the attention. Continue further with the modern control applications and all in the next class actually. Thank you.